Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if those fancy AI models we hear so much about can actually understand the charts and graphs that scientists use to show their findings? Today, we're diving deep into a really cool study that tries to answer just that question. It's about building benchmarks for large language models, or LLMs, which are the brains behind tools like ChatGPT. But this isn't just about AI. It is about how we measure what these AI models can do, and how we can trust those measurements. The researchers here are looking at whether AI can interpret complex graphs used in education and psychology. So, what's the big idea here? Well, imagine you have a super smart AI that can look at pictures and read text. Could it look at a graph that shows how well a test question works and tell you what it means? That's the core question this paper tackles. It's not just about seeing if the AI can spit out an answer, but how it gets there and if we can trust its interpretation. Think about it like this. Building a benchmark for an AI is kind of like creating a test, but the person taking the test is actually the AI model itself. And instead of measuring a person's knowledge, we're measuring the AI's ability to understand specific tasks. The paper points out that this is different from how we create tests for people, where we're trying to measure things like intelligence or skills. The authors really emphasize that when we talk about AI performance, we need to be super careful. Just seeing a high score on a benchmark doesn't tell the whole story. A single number can hide a lot of important details about how that score was actually achieved. This is where the social science perspective comes in. Experts in psychology and education have spent years figuring out how to build reliable and valid tests, and they bring that expertise to this new challenge of testing AI. Now, here is a key difference. When we test a person, the object is the person. But when we test an AI, the object isn't just the AI model itself. It's the whole setup, the specific model version, how it's connected, the instructions it gets, and even things like the image quality it is looking at. They call this a configured system. This is super important because if you change even one little thing about the setup, the AI's performance can change. Another mind-bending idea is how AI responses work. Unlike a person who might answer a question a certain way every time, an AI can be a bit, quirky. Because of how they're built, they can sometimes give different answers to the exact same question, especially if they're trying to be creative. They might also refuse to answer or give an answer in a format that's hard to understand. This stochastic nature, meaning it involves randomness, makes testing AI tricky. To show us how all this works, the researchers created a specific benchmark called IRT-Viz-Eval. It's designed to test if AI models can understand graphs used in something called item response theory, or ERT. Is a way psychologists and educators figure out how difficult test questions are and how well they measure what they're supposed to, the IRT-Viz. Eval benchmark uses a lot of these specific graphs. Here is where it gets really clever. Instead of just grabbing existing graphs, they generated them. They created the mathematical basis for these graphs and then rendered them in different visual styles. This allowed them to test if the AI understood the underlying math, even if the graph looked a little different each time. It's like showing the AI the same recipe but in different cookbooks. This idea of showing the same math in different visual styles is what they call invariance. It's a way to check if the AI is truly understanding the core information, or if it is just getting tripped up by how the graph looks. If the AI gets the right answer when the graph is bright and colorful, but then gets it wrong when it's in black and white, that tells us something important about its limitations. It's not robust. They stress that a single image or even a graph isn't the whole benchmark. A complete benchmark involves the image, the specific instructions given to the AI, the format it's asked to respond in, and all the details about how its response was recorded and scored. This entire package is what allows researchers to build a clear argument about what the AI can or cannot do. When it comes to scoring, it's not always a simple right or wrong. For some parts of the graph, the AI might need to give a specific number. The researchers designed a scoring system that gives partial credit for answers that are close, not just perfect. They also looked at the AI's rationale, basically the explanation it gives for its answer. This helps them understand if the AI is just guessing or if it's actually reasoning. Before they even tested the real AI models, they ran some simple tests to make sure their whole setup worked correctly. They used an oracle, which always got the right answer, a noisy baseline that gave answers that were a bit off, and a blind baseline that just gave generic guesses. This was like a systems check, making sure their measurement tools were working before they put them to the real test. When it came time to test the actual AI models, they had to choose how to connect to them. There are different ways to do this, like going directly to the AI company or using a service that connects to many different AI models. This choice is important because it can affect the results. They chose to use Hugging Face inference providers, which is like a central hub for accessing various AI models. They then administered their benchmark to 5 different vision-capable AI systems. Each system got all 198 tasks. They carefully recorded every detail the model used, the exact time they accessed it, how long it took to get an answer, and the raw output before anything was scored. This meticulous record keeping is crucial for making sure the results are reliable. Okay, so what did they find across the board? 2 models, QWN 2.5 VL72B and QWN 3 VL30B, scored the highest. But here's the really interesting part. Looking at the scores for different types of tasks revealed that no single AI was the best at everything. One model might be great at reading probabilities, while another excelled at identifying peaks in information graphs. This is a super important takeaway. Just looking at an overall score can be misleading. The task profiles, which break down performance by specific capabilities, showed that the AI models had very different strengths and weaknesses. So a model that scores high overall might be weak in a specific area that's really important for a particular job. Interestingly, when they looked at how the AI performed across different visual styles of the graphs, the scores were much more similar. This suggests that while the AI's understanding of the core math is important, its ability to handle different visual presentations can vary. The paper also talks about potential problems or threats that can mess with the results. One big one is contamination, which is when the AI might have already seen the benchmark questions or similar data during its training. This could make it seem like the AI is smarter than it actually is because it's just memorizing rather than truly understanding. Another threat is prompt sensitivity. This means that how you word the instructions you give to the AI can really change its answer. A small change in wording might lead to a completely different result, which makes it hard to know if the AI truly lacks the skill or just misunderstood the instructions. We touched on stochasticity earlier, the fact that AI answers can vary, but also the AI models themselves are constantly being updated, sometimes without a clear announcement. This version drift means that a benchmark that worked yesterday might not work the same way today. Keeping track of when you tested and which version you used is vital. And of course, there is the risk of scoring error. If the way you score the AI's answers is flawed, then your results will be flawed too. Even using another AI to judge the first AI can introduce its own biases. Finally, they warn about overgeneralization. Just because an AI does well on a specific benchmark, like understanding synthetic graphs, doesn't mean it is good at real-world tasks or that it is safe to use for important decisions. This relates to consequential validity, thinking about what happens when the scores are actually used. So, what's the takeaway for us and for anyone wanting to build their own AI benchmarks? The paper offers a clear 10-step recipe. It's all about being super methodical, starting with a clear goal, carefully designing the tests, and being transparent about every step. It's less about just downloading a dataset and more about building a rigorous measurement system. The IRT-Viz-Eval example shows how this structured approach pays off. They could generate exact answers, test how well the AI handled different visual styles, keep track of all the details, and analyze errors at a granular level. The real-world tests with 5 models highlighted how much differences in performance, output quality, and even how fast the AI responded can affect the overall results. Now, it's important to be clear, this benchmark is a fantastic tool for building and testing AI evaluation methods. It's not claiming to be a perfect measure of some inherent AI intelligence. The authors are very careful to point out that their results are specific to the conditions of their study and don't automatically translate to real world. High-stakes applications. They emphasize that future research needs to do more validation, especially by having human experts score the AI's responses and seeing if benchmark performance actually predicts real-world success. So, what does this mean for us? It tells us that when we see those impressive AI benchmark scores, it's crucial to look beyond the headline number. We need to understand how that score was achieved, what specific tasks the AI was tested on, and what its limitations might be. This research is a great step towards building more trustworthy and transparent ways to evaluate the AI that's becoming such a big part of our lives. What do you all think? Are you more aware of the complexities behind AI benchmarking now? Let me know your thoughts in the comments below. And if you found this breakdown helpful, please hit that like button, subscribe to Rubin's Mind Lab for more science insights, and ring that notification bell so you don't miss our next deep dive. Thanks for watching, and I'll see you in the next video.